Hello everyone, and welcome to Women in Operations Research and Management Science webinar, Worms and a Work in a Time of Coronavirus, presented by Susan Sanchez. This webinar is the first one in a series of Worms webinars that Worms board members are preparing for you. My name is Maga Kachatyan, and I'm 2020 President of Worms. Before I introduce our speaker, I'd like to draw your attention to Worms Forum and the Informs organization. The goal of the forum is to educate public about issues and opportunities impacting parity in society, especially relevant to organizations relevant to ORMS. How to create environment where both women and men bring their best by supporting and advocating for each other. We also like to create an environment where members of WORMS feel as themselves as a community by getting to know each other and celebrating each other's success. For that reason, we are organizing digital social, Worms digital social, which we had last month, very successful, and we're going to have it one next month, and webinars like this. Worms is active in several platforms. I'll post all the links in the chat for you to follow and be active and engaged. Please be engaged in our conversations. Please post in our social media. We want to see you. We want to have a conversation with you. And if you are not a WORM member, we invite you to join us. Here are the steps to follow to become WORM members. In fact, if you will follow all of these steps, you can modify your membership at the WORMs, at the Informs, and become a member of any society section of forum. We will share these slides along with the recording. And now I'd like to get back to our webinar and introduce Susan Sanchez, who graciously agreed to be our first presenter. Susan Sanchez is a professor of the Naval Postgraduate School. She has received the highest WORMS award in 2018, Awards of Achievement of Women in ORMS, and we announced that award at the so popular WORMS luncheon at the 2018 Informs Annual Conference. And this time I'm going to hand the floor over Susan, who is going to start the presentation. Susan, it's all yours. I'm stopping sharing so you can share.
Thank you, Maga. Thank you, the rest of the WORMS officers for inviting me to go ahead and do this. I'm going to try to cover a lot today in a short period of time, just to give you a flavor of what I've been doing in the last few months during the stay-at-home shelter-in-place situation. Point out at the bottom, these are my views here, and so please don't take this as official policy or position of the Navy, Department of Defense, or the U.S. government. So I'm going to have two parts to the talk. The first talk, I will discuss some work that I'm currently doing about the coronavirus, and we are just in the process of going ahead and working with others, both within the U.S., in the Department of Defense, and around the globe with colleagues in New Zealand, to go ahead and expand the suite of models that people are using to try to address this global crisis. So the bottom line up front, at NPS, we've developed a data farmable pandemic model, which is stochastic, discrete event, epidemic simulation model. And it's got some behavior that's very different from the classic epidemiological models. And that's what I'm going to show today. We did this to make something that's scalable from both small to large populations. And it's set up from the outset to be what I'll call data farmable, which means it's very easy to run large-scale experiments and gather the data from that in order to gain insights. So we're looking at expanding this so it can be used to help rapidly assess risks or benefits of various types of interventions in either as mitigation efforts or relaxing some of the social distancing policies that are in place. I'd also like to talk about data farming and your models. So I'm hoping not just to show you what we're doing here with the COVID, but to get you thinking about how these tools, this approach might be useful for your own work. So efficient design of experiments is really the key. It provides an opportunity for structured what-if analysis. And the bottom line is that after spending a lot of time and effort trying to get a model that is working well, this can be a way of letting that model work for you and gaining more insights. Then in the second half of the talk, I'm going to switch over and talk a little bit more about some of the more personal issues about work-life balance and in light of the current situation. So our model is in the class of compartmental models. This is a very classic epidemiological model. And one popular one is something called a SEER model. So the individuals in the population go through this idea of being susceptible to a disease, exposed to it. After some time, they become infectious. And then later on, they're removed, which is either recovered, typically assumed with immunity, or unfortunately passed away. And so any of the curves that you've seen about flattening the curve in light of the coronavirus, often those are based on these underlying SEER models. So we're looking at what's going on or what's projected to go on with that disease progression. Up in the top right of slide 3 here, we've got just a little graphic. This is a very easy model to implement in a discrete event simulation. And so
Susan, I'm sorry, I don't see your slides forwarding. So I still see the first slide.
Oh.
I'm not sure if it's me or everybody else, but oh yeah.
Same as here, Susan. I see all
so
that.
I didn't know if you promote them.
It says sharing is paused. Bring your shared window. Oh, okay.
Yeah, I think you're sharing your screen, but we don't see you promoting slides.
Well, I don't know what went wrong between yesterday and today.
I don't. It can be like double screen sometimes with presentation. So
no, I've just got
can you
one.
maybe unshared and shared again, and then we'll just see it?
Maybe you want to unshare and share screen again. Yes?
Okay, do you see a different picture?
Yep.
Yes. Compartmental models.
Yeah,
yes.
You want to go one back and one forward, see if it's moving? Yep, it's moving. Great.
All right. All right, so there was my bottom line up front slide, which I talked to. Compartmental models, now we can see that, again, these are a relatively simple model structure in the discrete event paradigm. And these curves are being used, among other tools, to go ahead and try to project how well our resources are going to be able to handle the healthcare crisis, and again, try to flatten the curve. Like other SEER models, ours should not be looked at as something to be used for prediction right now. It's there's so much we don't know still about this this disease. There's so much uncertainty in the world, but it is a model for gaining insight. So one of the reasons why we built this different model is that the world is inherently stochastic. And when we look at the classic serum models, they're based on deterministic behavior, differential equations, and everything projects at a constant rate. When we start looking at this from a discrete event modeling paradigm, we see that what we find are situations where we get fizzles and flares depending on the basic transmission rate of the disease. So in the left, we've got a situation with a low transmission rate, less than 1 typically means that an epidemic is not going to take off. So in this case, starting with a population of 50,000 people, we see that on average we get just under 4 people that are infected with this transmission rate of 0.8. As we start looking at the higher transmission rates, 1.4 or 2, we see that from these histograms that we get very different looking behavior. So with a transmission rate of 2, which is still, which is considered very high, although it's much less than they think COVID is, that we still have about a 30% chance of that epidemic fizzling and giving us a small number of patients infected. We also have a sizable chance of it jumping to a very large number of infected. And I apologize, I think I said a population of 50,000 before. This model was run with a population of 100,000 to start with. And what we see, if we look back at the previous slides, is that the mean reported, so in this case, the mean of 44,000, is not close to either of those, not the fizzle or the flare distribution. So if we're thinking about how to use that mean in order to set resources that are going to be needed for ventilators, for other type of health services, then we may be very off in one direction or the other. And so that stochastic nature is something that is important to consider. I've gone ahead here and done some runs of our model. This is notional input, so some of this I've tried to go ahead and pull in characteristics of the disease as much as we know, but some others there's, again, just a lot of uncertainty about. But what I want to show here is the tremendous difference that we get by looking at how these individual runs of the simulation might get. So the average behavior is this dark dashed line, and that follows very much the same trajectory that those deterministic curves look like when we're talking about flattening the curve. But we can see from the individual trials that we get peaks in terms of the total number of infected that change both in where they're located over time and how low and how high they are. And along the bottom, less noticeable, we see that we also have some fizzles where the disease maybe dropped to 0 quite quickly, and from that point on we had no more spread. And the effect that that has is, again, to pull this curve down. So we can think of this, again, as a way of trying to frame what might happen as we start looking not just at a global scale where deterministic models may do a good job in terms of evening out some of that random behavior for global level decisions. But if we're looking at local situations, so a number of similar, be they communities or companies or ships or elementary schools, how a disease might progress through those over time. So we're just trying to go ahead and get a sense that that stochasticity matters. Now, this was an initial excursion. I haven't shown a case where there's no intervention. What I did here in our model is to go ahead and say at day 10, we're going to drop that transition rate from 3.5 down to 1.75. We're going to make it 50% lower. So you could think about that as some type of intervention that might have been social distancing to try to cut down and flatten the curve. The reason I don't show with no intervention is because in this, this example, things just explode, and we would end up with only seeing part of the curve. It wouldn't be coming down. Now let's look at a more aggressive excursion. So here we still have the same population size, just a single initial infected individual. Basically, the only other things I'm changing are the intervention time at day 7, and I'm looking at that new transmission rate dropping by 75%. So this is quite an aggressive clamp down on that spread of transmission. And we see that we've got far fewer infected at any single point in time. So the maximum here is up at 20, where on the previous slide it was up in the hundreds. And we also see that there are a lot more cases. We see a little bit more detail about how quickly things drop to 0. So this is just trying to say, as we think about what coronavirus is doing in our communities, in our workplaces, we have to recognize that there's this high degree of variability out there that not all the models are going to project. Let's look at these in another way. So here I'm keeping track of the cumulative number of infected versus day for these 50 runs. And on the left, we see that initial excursion. Out of 4,000 people, we're going to end up with basically over 2,500 that are infected at some point during that period, even with that 50% drop in transmission rate. Over on the right, we go ahead and see that with a more active intervention, we're able to cut that down to 90. So quite a bit of difference looking at the randomness as well as looking at that average behavior. And in the graph on the right, our average is at least now kind of within the realm of where most of the data falls, instead of being in between different modes of the distribution. So that's our basic model. Now, what am I going to do with a model? I'm going to do some data farming. And more people have heard of data mining than data farming, but the term data farming has actually been around in the defense community for several decades. And these metaphors we can think of by contrasting it with the real world. So in the real world, miners are going to seek buried nuggets or veins of ore, but they don't have control over their environment. So how hard it is to find it and separate it out and be able to use it. And that was the impetus for the data mining metaphor, which is where analysts are seeking valuable information, those nuggets of information buried within massive amounts of data. But again, they may not have any control over how that data was collected, what's the quality of the data, how hard it is to find those nuggets of information. And in contrast, farmers go ahead and cultivate, they manipulate their environment to try to maximize the yield. Pest control, irrigation, fertilizer, different types of soil, different types of seed. And so trying to stay away from the fertilizer analogy too much, in data farming, we try to manipulate simulation models to advantage with designed experimentation in order that it is easier to get insights out from that data that we generate. And although I say simulation models here, this applies to any computational model or analytic model. Anything that you can code up on a computer, you can go ahead and do data farming for. And we've been doing this for a while now. We generate a lot of data. We look at big data, and that's important for addressing big questions. So let me look at just a little bit the background behind data farming. I love this quote, although it's over a decade old now, from the New York Times. When the first petaflop computer, supercomputer, came out that could do a quadrillion operations per second, it reported that this would fundamentally alter science and engineering by allowing us to perform experiments that would previously have been impractical. But that experimentation is hard, even with supercomputers. So if we had a model with 100 different input variables, 2 levels for each of those, and our simulation model ran in a second, it would still take many, many times the age of the universe to go ahead and finish that experiment, even with petaflop computers. So 2 to the 100 is just computationally intractable. And of course, in OR, we understand that cursive dimensionality. It's not going to be cured by Moore's laws. And it is something, however, that we can address with data farming and with large-scale designed experiments. So my methodological work for the last couple decades has focused on trying to come up with better ways of setting up and analyzing these large-scale experiments. So let's go back to our pandemic model. As I mentioned before, it was set up to allow me to easily go ahead and automate the process of running the experiments and generating the data by simply using some different scripts to quickly generate designs, and then other scripts to go ahead and automate running the process. So instead of just looking at a couple excursions, I ended up looking at nearly 1,100, 50 replications each. That took less than 3 minutes on my laptop. So I didn't even have to make use of the computing clusters that I often do. And from that output, I'm able then to fit meta models to characterize my simulation model's output behavior. So the simulation model is a model of reality. It's a complex model, complex output. We're going to try to simplify that with a statistical model. So in this case, went ahead and simply looked at a logistics model for whether or not the epidemic fizzled or flared based on the cutoff I chose was that if more than 10% of the population ended up getting infected, then we would count that as a flare. Otherwise, it would be a fizzle. And from those models, then, from the data farming, we can do lots of things. One that doesn't show here, because I did just a small experiment with a small number of factors, is that this will screen out and show us what the key drivers are. So we regularly look at models with dozens or hundreds of different parameters, different factors that we can manipulate. And it's helpful then to use these analytics to pull out what are the key drivers and the key interactions of the model's behavior. In this case, I've just gone ahead and shown a few different excursions that we get here. Using the software package that I was, this can be done interactively. So the whole model analysis process just can be very, very rapid to try to look at some of those what-if questions and see what might matter. Another type of tool that we like to use for this in decision support is something called a partition tree. So here I take all that raw data, my 54,000 runs of the model, and put it together and look at these different factors. And then a partition tree is going to go through, it's a data mining technique that will automatically say, let's take that data, let's look at all the potential factors we might use to split it into 2 groups, not necessarily of equal size. And let's pick the split that maximizes the amount of explainability there is in the model. And since we've set this up as an experiment, we can even talk about it as cause and effect within the context of our model. So moving down the left, we see that if we're able to get a transmission rate reduction of at least 70% over the variety of situations I ran, for instance, yeah, just varying these things quite widely. We're able to cut down and get good outcomes where we have just 200 or so people infected. On the far right, if our transmission ratio reduction, we're not able to damp things down so low, then particularly if the population that we started out with is large, we're going to have a very large number of people infected. So here over 4,600. And you can see in the middle, you know, there are trade-offs involved as well. So just because we started off down a good branch doesn't mean we necessarily get to a good location and vice versa. So this is a quick way of revealing the trade space. We can use partition trees either to look at what makes a difference in the epidemic. That might be helpful in trying to determine what data we need to collect about the disease or so forth that would be most relevant to certain questions. Or it could focus on just using the decision factors. So we know that the transmission ratio itself, which is down at the bottom, the second split on the left, that's something we cannot control. That's what nature has given us. But we can find out whether it matters or not. But we can also do trees where we just say, you know, what's the best we can do with what we know. So this is also a way of looking for robust solutions. So we're currently underway, as I said, we're working with a number of others to try to use this model to help the decision-making process as we look at moving forward. I won't go through these all, but just to let you know, we're working on this and hoping to get some results out very soon. I would encourage you to think about doing data farming for your models as well. And so just point out our website here. It's a little bit out of date. I was going to check that everything was updated before this webinar, but my work-life balance hasn't been in as it should be. So that'll be coming up soon. So with that, rather than stopping for questions, I'm just going to barrel ahead and get to the second part of this talk. So I just talked about the work I'm doing related to coronavirus, and now I want to talk about what informs and what worms can be doing as we look at how coronavirus is affecting our work lives. So looking back, OR is the science of better. We can look at making decisions to save lives, save money, solve problems. And in general, this is an ongoing process. We can keep moving from identifying a problem, creating a model, analyzing it, solving it, implementing the solutions, assessing how well they work, and continuing. And of course, a lot of communication and teamwork back and forth in all aspects of the problem. So I started thinking about lessons learned in OR. What are some of the techniques that we can take from OR as we talk about work-life balance issues? And the first question, or the first lesson learned from OR, is to tackle the right problems. So how do I achieve work-life balance? That can be a good problem for an individual. I would argue that's a better problem to try to tackle than how do I try to do everything possible with just less sleep. And at the same time, if we look at it from an organizational perspective, the fact that it is work-life balance means that that work supervisor, that work administration also needs to be involved. And so certainly I'm speaking more from the academic side, which is where I'm coming from, but I know the same thing applies in industry as well. This is really a time where we have to help mentor, help support our junior colleagues. And the coronavirus has thrown everything upside down in terms of the work environment. This is affecting both genders, men and women, but we have to take a look. We have to make sure that we're trying to address the right problems. Modeling assumptions matter. Another important lesson. And here, I just wanted to bring up a few things where these assumptions can make a difference. So some positives, some negatives. Positives, OR makes the list of top 10 STEM professions employing women. So that is something that's very positive from a few years back. We still see, however, that we've got things like a gender pay gap in different professions. And I've seen a number of articles in the popular press where they will talk about the assumptions. It's stated or it's sort of understood that the women are going to have the lower paying jobs, and that might be why they are responsible for taking over more of the housework or more of the homeschooling in the current situation. And if that's the assumption, that's something that is true in some segments of our society, but I don't believe it's true in ours. And at least not to the same extent. And this is a case where I would like to change the dialogue and help put Informs forth as an example of professions that are, I'm losing my train of thought here, sorry. But really to go ahead and say, let's start working from different assumptions. We can be the trendsetters. We can be the ones that set examples. And this article from Organization Science is one. The title is looking at a gender penalty in terms of adding women to the board of directors for a lot of industrial companies. But, and that's a negative message, and that they were able to show that there were penalties given to those companies initially. The positive part of that article talks about the fact that by articulating the assumptions that the women weren't being put on there just to have diversity, which was sending one kind of signal, but the women were being put on there because they had the right skills, leadership capabilities, and so forth. That is a way to overcome those assumptions. So let's look over our assumptions. Let's make sure that we're not just falling into the way things used to be. Choose the right objective function. Avoid something called a type 3 error. So here we've got a lamppost, and there's an old joke about someone is looking around on the ground under a lamppost, and a person comes up and help and says, "What's going on?" And they say, "I lost my keys, I can't find them." He says, "Did you lose them here?" And the person says, "No, I lost them over there, but it's too dark to look over there, so here's where I'm looking." So we want to always make sure that we choose the right objective function when we're going ahead and looking at our solving our problems. And a great example from the time I was an undergraduate student, I remember an OR faculty member saying that they'd been called to by a prison system to say, we want to reduce recidivism, and they said, that's not what you want. You want to reduce criminal behavior after a prison term, because reducing recidivism might just mean training these, in this case, juveniles, to do a better job of breaking and entering without leaving fingerprints and so forth. Integrity matters in modeling and data, in communication, and so that's important both as we look at what we do in our workplace, and as we try to come up with better structures and solve these work-life balance problems within our families and within our workplaces. And that communication, that integrity can help us, I think, identify where we have common ground, while still recognizing that even informed, well-educated, well-meaning people may still have differences of opinion. But if we can fill that out, then we can go ahead and establish that communication to hopefully move towards better solutions. Greedy algorithms are usually suboptimal, and so just because one person in the household, maybe my husband is a better cook than I, doesn't necessarily mean he should do all the cooking. And so we know we're well used to problems where we realize that with constrained resources, we've got to use a mix of opportunities. We've got to use everything wisely in order to come up with good solutions. So that's one thing to keep in mind as we start looking at how to redefine what our workplaces are like, how to redefine what it is like to teach in a totally online environment, 24/7. What is it that we're going to do to try to come up with solutions that aren't defaulting to the idea that we're only going to go for what seems to be a quick win. And the other thing I want to mention is that coefficients can change. So we know whether it shows up in our LP or not, we know that those objective function coefficients, we know that those efficiency coefficients, the right-hand side coefficients, those are things that can change over time. And so if we've got some really binding constraints, we can look at other ways of trying to improve the system. Short-term and long-term solutions differ. I'll just put back the these flatten the curve pictures again. We've had to act very rapidly to go ahead and address the immediate needs of the crisis. We're going to have to start looking towards the future and see what more we can do as we move forward. And again, in OR, we're used to this. We deal with rolling horizon problems. There are all sorts of situations where we are used to this idea of saying the type of problem that we're looking at, the type of solution we come up with may depend on the time horizon that we're looking at. There are lots of different solutions. I will hope that with regard to work-life balance, we are trying to find, at a minimum, feasible solutions and not sticking with infeasible solutions, but also recognize that there are multiple optimal solutions. And so there's not going to be a one-size-fits-all measure for every household or for every organization, but let's go ahead and try to work towards coming up with a set of good solutions to address the complicated problems that we have. How am I doing on time? I'm going to charge ahead. OR lessons learned, it's an ongoing process. My first academic job, my husband and I, both academics, so we had more flexibility than many, but our university had no childcare, no childbirth policy for faculty. No maternity leave, no paternity leave, nothing related to tenure clocks and so forth. So one thing that I was very proud of that Worms helped spark and promote in the 90s was the idea of tenure clock extensions, and to go ahead and help account for the fact that we no longer were in a situation where most faculty who had children also had a stay-at-home spouse to take care of those, but two-family careers were becoming much more prevalent. And There's been some recent studies that have shown, at least in certain fields like economics, that that has backfired, and that has actually led to more of a gap between the likelihood of men and women getting tenure. So problems need to be revisited from time to time. Maybe we need to look for additional solutions or assess how well some of those solutions are working. Maybe it's time to take the next step. So we initially made great gains, and now it's time to eke out the rest. And again, I think in the OR community, we're used to this idea that not everything can be solved in a day. So you have people that may spend their careers working on improving solutions to certain classes of problems. I firmly believe that when times are hard and when the problems are challenging, that's when OR has a chance to really shine in the analytics field. And our world is facing massive problems these days. So we need to be thinking about what we can do as a profession so we're better able to address those challenges. And part of that, I believe, is making sure that our junior analysts, be they in academia or industry, our colleagues, that we have the time, we have the energy to address these problems without burning out. And so in the academic side, I even think the whole idea of tenure is something that we should look back and revisit and see if we are solving the right problem. Tenure was supposed to grant academic freedom. With more academic freedom would come the chance to move into interdisciplinary areas, address some of these big challenges, and is the way that's being implemented these days supporting that or delaying that for some of our colleagues. Proactive is better than reactive. Very different if we're solving a facility location problem or simply looking and saying, after we've set up our facilities, now we'll figure out whether or not that was a good place to put them. So I think now is the time to support the next generation of OR professionals and try to make sure that they are set up for future success. And communication is key. So with your team, with your partners, with your family, with your supervisors, with stakeholders in your research, and in society. And there's a wonderful article here. If you haven't read it, I encourage you to do so, on looking at the many different ways that women leaders have addressed the COVID crisis responsibly. And the 4 things that are called out in this article are truth, decisiveness, tech, and love. And so I think these are, again, right within our wheelhouse in terms of our profession. So I'd like to say that if we take this time, and we are in a new world, let's hit the pause button for a brief minute if we can, and start to think about what is it that would make life better in terms of this work-life balance. What do you need? What will you do at home or at your workplace or in your community? And that could be as simple as, what will you do? I will reach out to somebody if I need help and let them know that I need help. I've been very impressed with how proactive our administration has been at NPS at reaching out and communicating with faculty, staff, and students and saying, we don't know what's going on in your lives. Let us know how we can help. So if I were doing this in a big room live face-to-face, I would ask everyone to to stop. Well, I'll still ask. Take 30 seconds and try to think of something that you would like, that something that you need, or something that you would do in the next month. So I'll just wait 30 seconds here. And normally I would say, turn to your neighbor and tell them what you have, what that's going to be. I'm going to ask you instead that after this webinar is over, that you talk to someone else or send yourself an email, write it down, what that could be. So I don't have the answers, but I think it's an exciting and important time to be looking for solutions. So with that, I'd like to turn it over to questions.
We have several questions that have been submitted by the audience. And as a reminder, if you have a question that you can submit in a chat box or raise your hand, you'll be called out for to ask the question. So we have a question that says, could you go through the assumptions you considered for your model?
So we do have a paper with the model. So the link for that is in the slides, and you're welcome to go and look at that. Very quickly, what we're assuming is that each individual going through this disease progression is going to change state at some discrete and random point in time. So we're actually generating those times. So a time, for instance, between when you're infectious and you have the chance to expose somebody else. One thing about this model is we can use a variety of different distributions. So we're not assuming that everything is memoryless. We are not putting together a specific network of how individuals react to each other with social contacts, but we're basically generating a set of close contacts on the fly and doing that with a drawing from a Poisson distribution for the number of contacts. And that could be changed. All our distributions can be changed. We can change not just parameters of distributions, but distributions themselves. So generally speaking, we're going to have random amounts of time where individuals are infectious or exposed or go to removal, and then that is we'll let the simulation run. Some of the interventions that we're looking at right now are going to be, we're trying to expand it. So instead of just intervening at a fixed point in time, we intervene because, for instance, we reach a certain level of exposure or things of that sort.
Thank you. There is another question. How are you using the word excursion here? How do you define that word excursion? Maybe there are models within the meta models, or are they just experiments?
So the excursion actually is a term that's often used within the Department of Defense, and I briefed these slides yesterday morning. And so you can think of that as just being a scenario. A particular scenario, a particular set of inputs that we're looking at for running that simulation. So normally I would have said something like a baseline scenario But as I mentioned in the talk, the baseline was not interesting in terms of showing the curve because it's just so infectious that it doesn't die off.
Thank you. And there is another question. How can the model be validated?
How can the model be validated? Validation is an excellent question. One of the benefits we have with data farming is that when we do these large-scale experiments, you can view those as a massive sensitivity analysis. And so, we're all making assumptions when we put together models. And so if we're thinking of it from the decision standpoint, we would like to be making decisions where if we were off just a tiny bit in terms of, say, that transmission ratio, that doesn't flip us from making a good decision to a bad decision. So I would say one of the ways we look at trying to validate these models is to go ahead and see how sensitive they are to those different assumptions. In the simulation field, certainly there are a lot of times where what we have been dealing with are problems where we cannot validate things. If we're looking at the future, even something like saying we want to look at a future factory layout, we're not going to be able to validate what might happen we don't have the luxury of waiting for data. But there's a very interesting paper that from years ago from the Rand Corporation that talks about, I think it's 7 uses for unvalidatable models. And I think that's also an interesting concept in OR. But I would argue that with any model that we're looking at, that doing one of these data farming experiments is a way of at least understanding how sensitive your results are to some of those assumptions. And that establishes the credibility of the model, whether or not you can call that a validation. More specifically, in terms of some of the data sources, we're trying to tap into, there's a lot of excellent data that's being collected out there about the disease, and we're trying to tap into that to the extent possible.
We don't have any other questions at this point. Anyone raising hand? I don't see any. Well, thank you everyone who joined us. We have a couple of minutes if you have more questions. But otherwise, Susan, thank you for sharing your insights and expertise. There are a couple of comments coming in. Susan Ryan says, thank you. I'm so happy to see stochastic model of disease propagation. And then there was another comment that says, and nice, I hadn't seen that women leaders angle. I think that was on a slide where you showed all the women leaders of the world with positive impact on results, in the countries. Daphne answered. And well, thank you everyone who joined us for today's webinar. And thanks for your time, and have wonderful rest of your day. That would conclude our webinar. Thanks a lot.